Is there a difference between the limit of a sequence and cluster points of the sequence? Sometimes when we look at the formal definition, it's not always clear, especially to students who are just starting real analysis. So let's look at that by considering two examples. In this first diagram, we have a sequence x1, x2, x3, x4, all the way up to x8, and we'll assume that it continues on from x8. But observe the behavior of this sequence. When we look along the x-axis, so we're looking horizontally, we see that from x1 to x4, the sequence is kind of chaotic, like some are inside the band, that band label 2 epsilon because it is a band of width 2 epsilon. We observe that from x1 to x4, some items in the sequence are outside the band, and in fact only one of them are within the band. But after x4, everything seems to stay within a distance of epsilon from x. So this is how we would expect x to behave if x is in fact the limit of this sequence. Now, since x is the limit of this sequence, it does also fit the definition of being a cluster point. But not all cluster points necessarily have to be the limit of the given sequence. And to take an example, observe this sequence xn equals minus 1 to the power of n, where n is an integer. This sequence actually consists of two subsequences because this sequence alternates between the values 1 and minus 1. So it has a subsequence consisting of all ones if you take all the indexes to be even integers, and there's a subsequence consisting of all minus ones if you take all the odd integers as indexes. Now, each of these values, 1 and minus 1, are cluster points, but this sequence does not have a limit. So it has two cluster points and there's no limit. Now, these are two examples that we see represented visually, but how could we tell the difference if we look at the formal definitions of limit and cluster point? Well, a cluster point of a sequence is x such that xn minus x is less than epsilon for infinitely many values of n, the indexes n. And we can see that this is true for this sequence xn equals minus 1 to the power of n, because there are infinitely many indexes such that xn is equal to 1. Also, there are infinitely many indexes such that xn is equal to minus 1, because these are two subsequences in this original sequence. But if we look at the definition of a limit of a sequence, there's one subtle difference that a beginner might not notice. We do want xn minus x. If x is the limit, we do want xn minus x to be less than epsilon. But it must be true not just for infinitely many values of n, not just for infinitely many indexes, but for all indexes beyond some n, where n is some integer. So what it means is that the first big N terms, the first finitely many terms, even if big N is 5 million, we don't care what happens with those first terms. Those first 5 million terms could be very chaotic and it's okay. What we want to know is, let's say after 5 million, the sequence stays within that epsilon band. So a point is a limit point if after big N, all of the points of the sequence stay within that epsilon distance from x. And as we could see from these definitions, a limit, well, the limit of a sequence is a cluster point, because if all the indexes after a certain big N are such that all the terms are within epsilon of that x, then of course that satisfies the criteria of being infinitely many. But infinitely many in the case of a cluster point does not necessarily mean all, because as we could see in this example, there are infinitely many ones, infinitely many minus ones, but even though they are infinite, they do not equal to all the terms in the sequence. So by looking at these two diagrams, we could very clearly see the difference between the behavior of the limit of a sequence and cluster points of a sequence. And I would like to point out in this diagram that when we look horizontally, we can see that the points of the sequence after some xn, in this case x4, stay within the band. But how does this look if we look at it on the real number line? Observe that The chaotic points, let's call them that, that's x1 to x4, observe that they kind of stay outside. Well, actually x3 is also in there. But for x5 onward, they start to sort of bunch up around x, which is exactly what you would expect to see if we visualized what a limit, well, what the points around a limit would look like on the real line.